Let's now welcome on stage Andrea Sammartino, Project Coordinator Manager at Megaride, and Luca Veneroso, Control System Engineer at Meccanica42. Explore the cutting-edge advancements in driving simulation, featuring an innovative tire road multi-contact ride model. Witness the integration of this model into a real-time driving simulation platform based on a HiL steering bench, revolutionizing the driving experience.
Okay, so good afternoon to everyone. First of all, thanks a lot for being here and for your interest, and thanks to the Megaride for the invite. My name is Andrea Sammartino. I'm Project Coordination Manager at Megaride, and today, together with Luca, Control System Engineer at Meccanica42, we are going to introduce to you to a joint work concerning the reproduction of the real driving feeling with a specific focus on a haptic enhanced steering simulation based on a multi-contact tire model developed by Megaride and a hardware-in-the-loop steering bench developed by Meccanica42. First of all, a brief introduction about the companies. Megaride is a University of Naples spin-off company that was born in the fall 2016 from the Vehicle Dynamics Research Group. What we do is studying the interaction between the tire and the external environment, reproducing it by means of multi-physical tire models. We provide modular simulation platforms that are usable for lots of different application fields. So we support car and tire makers in order to speed up the development and prototypation stage of both tires and vehicle subcomponents. We work in hard real-time simulation platforms such as VA-grade car real-time in order to reproduce the real driving feeling. And as you can see also from the timeline below, we have a history of support to motorsport partners with good results starting from the fall 2017, supporting Audi Sport up to the most recent great result we obtained in Formula 2 and Formula 3 championship.
Thank you, Andrea, for the introduction, and good afternoon, everybody. Meccanica42 started this activity in 2015 with the aim to expedite and facilitate the introduction of advanced vehicle systems. And this is achieved by introducing into the development process advanced hardware-in-the-loop solution and providing high performances on board devices. The first product line of Meccanica42 is real-time test benches, and here we have the possibility to integrate into the simulation loop several vehicle systems and enable integration activities, tuning activities, and also the assessment of other functionalities, while with onboard devices we are capable to control and monitoring the vehicle states in real time. With real-time test benches, we introduce into the simulation loop the steering system and the brake system with the HiL and brake HiL test bench, and also the front ADAS camera with CAMIL. And all these test benches can be connected both to static and dynamic simulators, thanks to our remotization technologies, and especially the SMC, that stands for steering motor cubes, enable the remotization of the HiL test bench. While with our onboard devices, in particular with the power steer actuator and the corner brake actuator, we are able to control the steering system and the braking system of the vehicle.
Okay, let's move forward to Megaride multi-physical platforms that goes under the name of Ride Suite. When we talk about tire modeling, we used to promote a holistic approach because all the complex phenomena occurring at tire road interface are deeply interconnected, interlinked with each other. This is why Ride Suite was born. It is a modular platform that comprises of 4 elements, each of which is able to simulate a specific phenomenon occurring at tire road interface. So we have a real-time tire thermal model. We have a multi-contact tire model that is the focus of today's presentation. We have a wear model able to provide us insights on both the wear abrasive phenomenon and chemical degradation. And finally, we have an MF-based infrastructure that, of course, is sensitive not only to standard input of the tire modeling, but also to additional physical information provided by the other modules. The models are easily parameterizable. and we exploit non-destructive characterization to parameterize the model that can be fastly carried out at our facility at the University of Naples or by means of innovative devices such as the Vesevo that we have at our booth. Let's focus on the 3D ride. That is the module of the ride sheet that is deputed to the reproduction of the real contact between the tire and the road micro and macro asperities in order to enhance the real contact feeling in hard real-time environment. As we are going to see, thanks to the results that we are going to present, it can be demonstrated that we have an improvement not only towards the vertical dynamics and thus ride and comfort application, but also from a global haptic point of view, so also handling behavior of the vehicle. The model was thought to overcome the typical issue of the single point contact model, and basically it stepped in at the contact patch, where we need to evaluate the right kinematics input for the tangential dynamics module, taking into account of the right inclination of the road plane. Of course, everything is multiphysical, so it is not sensitive only to standard input, but also to the tire thermal state and the wear state. So everything is deeply interconnected at the contact patch. From a modeling point of view, which is the approach to overcome the single point contact, it is a multi-cam approach that, with respect to the single point contact model, that generates an instantaneous variation of the center of the contact patch 8, is able to provide the right direction of forces propagation from the contact patch up to the wheel lab. So by means of a multi-contact physical model, we are able to correctly reproduce the gradual center of contact patch 8 variation when the tire encounters an irregularity. From an IO point of view, of course, we need the road profile characterization because we need to carry the road points, as well as a structural, non-destructive characterization of the tire with a specific focus to the contact patch. It's important to model in a correct way the contact patch by means, again, of non-destructive methodologies because according to the position and shape of the contact patch, the cam will change their shape and their dimension. The output is a smoother signal that is more in accordance with the experimental data and that is able to reduce the noise that the single point contact generates and is able to provide the right feeling when we go from a road with a certain roughness characteristic to another one, or for example, if we impact on a macro asperity, such as a different curb for motorsport application, or even, for example, sidewalk for passenger application.
Thank you. So as we know, the development of modern vehicles heavily relies on the use of driving simulators, and this is to enable a human-centered design process. And due to the high effort that is required by iterative tuning activities of modern systems, the introduction of real hardware into the simulation loop proves to be a winning strategy, both in terms of cost and time savings. Moreover, several recent research demonstrates that the steering feel and especially the steering wheel torque plays a pivotal role in the subjective vehicle evaluation. So we start to investigate how we can improve the steering feedback during simulation, coupling the advantages that came from our technologies, so the VI-grade real-time vehicle model, the tire model, and the multi-contact tire model developed by Megaride, and our steering test bench. We start the activity with track test, and here we collected data both for tire model calibration and for test bench validation that represent the second phase of the activities. And the aim was to validate and verify the capabilities of the steering test bench to correctly replicate the operating condition of the steering system. And the last phase was a simulator session in which the driver experienced both the single and the multi-contact tire model replicating the same rain plan performed during track test. The track test session took place at the circuit of Sele, during the event of Seaside Racing. This event took place each year in this circuit that is located near Naples, and the event is mainly promoted by Megaride and the University of Naples. And here each partner share the measurement equipment and the collected data in order to research, in order to promote vehicle research. Okay, during track test, the research vehicle of Meccanica42 has been equipped with a front curvature motion sensor in order to quantify vehicle velocities and the slip angle. And the front wheel rim were replaced with wheel transducer to estimate the contact patch forces, and this data were useful for tire model calibration. And we also installed the steer sensor on the steering wheel to quantify steer torque, steering angle, and velocity, and apply the load cell on tie rods. The simulation station is composed for the validation test by the HiL test bench and the SMC that consists in a steering robot which is mounted on a fully adjustable frame to test various geometry. And the simulation is executed by the real-time machine, which has two main tasks. The first one is to generate the CAN messages for the steering control unit. And the second one is to control the actuators. So we have two actuators that replicate the thyroid forces on the rack, closing the loop on load cells. And the third actuator is the steering robot that provides the steering wheel input, and the feedback is closed on the absolute encoder. So we took the data taken from track test, in particular the load on the two thyroid and the time history of the steering wheel angle. So the load of the two thyroid represents the target for the two torque motors that apply, that replicates the forces on the rack, while the steering wheel time history represents the target for the steering robot. Here and for the next slide, the red line will represent the data collected during track test, while the blue line are the data collected with the simulator. And the first test consists in a sequence of low amplitude step steer, and here we have the comparison between the targets and the measured data for all the actuators. So on the bottom plot we have the comparison between the target thyroid forces and the measured one, and on the left top we have the comparison between the steering wheel angle, target, and the measure. On the top right, we have the validation data, so the comparison between the steering wheel torque collected during track test and the one collected during this validation test. And the second test is composed by 4 high amplitude step steer, and here again we have the comparison between the target and the measure, and here is clear the capabilities of the 3 actuators to correctly replace the target both during transient and steady state conditions. Here we have a resume that show the error distribution for the 2 thyroid torque motors, and on the left, so the error is defined as the difference between the target and the error. And we can see that they have a very similar error distribution, while on the right we have the distribution for the steering wheel torque and the steering wheel angle. We can see that the steering wheel torque has a wider distribution. This is because the steering wheel torque is the validation data, while the control data for the actuator was the steering wheel angle.
Okay, so the last step to complete the digitalization and validation process was to carry out a simulator session. In this case, the research vehicle brake unit has been integrated into the simulation loop in order to exactly reproduce the effect of the stock ABS and ESG control logic. And of course, with respect to the test bench validation, in this case, we exploited the real input coming from the human driver, both from steering wheel point of view and of course pedals, so accelerator and brake, throttle and brake. This is why we organized a dedicated test session at Meccanica42 facilities, putting the same driver who drove the real car at Seaside in the loop at the simulator and reproducing the same maneuvers with the same driving style that we performed on the track. So starting from gentleman driving, going on with pure interaction, up to max performance and sliding laps in order to explore the widest range of tire road interaction characteristics, conditions, from low level of slip angle up to the highest possible, both in linear and non-linear zone, and of course in pure and combined interaction. The points cloud obtained were useful to identify the tangential dynamic tire model. This can be fastly identified by one of our internal tools, that is the Ride Lab, and of course that is able to provide information also on the sensitivity towards the temperature, the pressure, and also the wear, that is the distinctive point of our models. So in the simulation, we put together, of course, the 3D ride model together with the advanced tangential dynamics model, and we could objectivize the results and the behavior of the vehicle. And the interesting thing is that we could couple the objective information coming from the data with the subjective feeling of the driver. So we could improve not only the vertical dynamics behavior, so ride and comfort, but also the tangential dynamics behavior. So the global handling of the vehicle was improved thanks to this enhanced haptic feeling that the driver reported, thanks to the multi-contact model. So the zoom that you see here highlights that by means of a multi-contact, multi-physical tire model, there is improvement in correlation with the experimental data. And we carried out this analysis also at different load configuration of the vehicle. So here you see, for example, a ballast configuration and an example of longitudinal acceleration correlation that demonstrates the fact that the driver could improve also the management of the braking pedal force thanks to the enhanced interaction between him and the steering wheel, between him and the global vehicle. Another interesting analysis that we performed was the activation of the ESG. The control logic used at the DIL is exactly the same that the OEM implemented on the real vehicle. And as you can see here, also the recovery and the global behavior of the vehicle demonstrated by the ESG activation point is improved. And the driver told that this was due to the enhanced interaction and to the enhanced haptic feeling between him and the external environment. Finally, another example of a crucial point that is basically the transition between the asphalt and the curb, and again the asphalt. As you can see here, with the single point contact model, both, of course, the target and the load cell are characterized by a spiky signal that is due to the single point contact model approach, whereas with the multi-contact tire model, we are able to generate a gradual variation of both the tie rod and steer torque that, of course, make all the difference in the global feeling of the driver when going from the asphalt to the curb and again back to the asphalt. So here you see the instantaneous variation of this quantity, whereas with the multi-contact tire model, everything it's more, let's say, smooth, gradual, and realistic. So just to sum up, we could demonstrate with this application that we could improve the haptic feeling of the driver, so we could improve the general perception of the interaction between the tire and the external environment. So the perception of the interaction between the tire and the road, not only from a rider comfort point of view, but also from a global vehicle behavior point of view. And of course, we want to add another step. So we want to add a Swift Evo modeling to the 3D ride coupling. So this new model that came out in RideSuite V24 with the 3D ride model in order to extend the range of validity of the frequency domain up to 1 kilohertz. Of course, we expect improvement also in this case, both for rider comfort application and handling point of view. So this is our contact. We hope you enjoyed the presentation.
Thank you.